So this is the continuation of the lecture delivered and uploaded in the YouTube link. So the earlier lecture name was Designing of Asynchronous Counters Lecture 1. So we'll continue from there. So in the last lecture, we have demonstrated how a designing of asynchronous counters can be done with a systematic procedure. So we have designed a mod 6 counter for the given sequence. So sequence had 6 states. So we have used 3 JK flip-flops, and the circuit what we designed, which comprise of a logic network, drives the JK inputs in such a way that the required states will be available at the output of the flip-flops. So summarizing the whole design what we did in the last lecture, any counter if you want to design using synchronous method, and if the sequence is not contiguous fashion, they are not binary sequence, so we have to prepare an excitation table. So in the excitation table, so we will write all the states required, and what will be the next state for every state we'll document it, and for all the flip-flops what will be the required JK for each state to get the next state will be documented with the help of application table. Then the last column will be the outputs for the inputs of the first column. So it's like a truth table. So we have derived the expression, algebraic expression for all the J1, K1, J2, K2 using a K-maps, and with whatever the logics we've got it for each of the expression. Using that we've built mod 6 synchronous counter with a JK flip-flop. Now continue from that. What is the challenge in these types of counters? Number one, so it is called as the counters sometimes enter into the states which are not valid states. Is the counters are designed for self-correction? That is what we have to introspect here. The 3 flip-flops used here will contribute 8 states. 2 to the power of 3 is 8 states. But the required sequence is only 6 we have taken it. So there are 2 states which are not valid or which is not part of the sequence. So what are those states? So we can see that in the previous in the discussion we have, these are the 6 states. The 2 states which are not available is the 4 and the 7. So you can see that 100 is not available, 111 is not available. Now by chance, if this counter enters into one of these states, 4 or 7, the question asked is, how does it enter when the system itself is not designed? There are 2 reasons why it can enter. Number one, when the power is first applied to the network, the initial state of flip-flops may be unpredictable. Hence, there is a chance when the power is up, you may get a state which has not been designed for that. Second reason, the noise signals, when the counter is operating, it's in the proper way it's operating, because of the external noise, it can get into one of the state which has not been designed for that. Now we have to prove that whether the counter which has been designed now is self-correctable or not. In the sense, by chance if it enters into any one of these states, does it come back to any one of the valid state, or it hangs up or lock out and it will never enter into any of the valid states? This we have to prove it. So what is the method to prove whether it's a self-correcting counter or not? Now let's document the invalid states. Now 100 is not a valid state, 11 is a not valid state. Now already we have derived in the previous discussion the expression for J1, K1, so Q2 and Q3. So Q2 bar is an expression for K1, similarly Q3 bar is an expression for J2, Q1 is an expression for K2, Q2 for J3, Q1 bar expression for K3. So I have written here the circuits which drive the J1, K1, J2, K2 and J3, K3. Now I want to prove that if 100 by chance it enters a state, what will be the next state? So let me calculate using the equation now. So 100 is unexpected state it entered. Now what will be the value of J1? Apply the formula Q2, Q3. So Q2, Q3 is 0, so that is 0 into 0, it is 0, comma. Q2 bar is what? 0 is there, so bar means 1. Similarly, So using the Q1, Q2, 3 values, using these equations, I have documented for J2, K2, J3, K3. Now, so once we know J1, K1, we know that what is an expected next state for the Q1. So I know J1, K1 is 0, 1. So what is the expected state at the Q1 after the clock cycle? Since 0, 1 is a reset state, it becomes 0. Similarly, for J2, K2, 1, 1 indicates a toggle state. So existing value is what? 0. So it toggles 1. So 0, 0 means it's a memory state. Whatever the value at the Q3, it should repeat in the next state 0. Same way. So we have calculated invalid same values, the different values for J1, K1, J2, K2, J3, K3 for another invalid state. Another invalid state 1, 1, 1. So applied the equations of J1, K1 and written the values or these inputs. Now let's take one by one. Now for the Q1, if the inputs are 1, 1, 1 and the J1, K1 is 1, 0, 1, 0 is set state, so that it will become a 1. Now for 0, 1, it is a reset state, so it becomes a 0. 1, 0, it's a state 1, so that it does not depend upon the present value. So because it's a set or reset state. Now, so we know that 0, 1, 0 in the counting sequence is a valid state. You can see that 0, 1, 0 is a valid state. Similarly, 1, 0, 1 is also valid state 101. So by that now we can declare that the counter whatever we have designed is a self-correcting counters. So this is how we have to verify whether the counter is self-correcting or not by documenting the present state, the expressions at J1, K1, J2, K2, J3, K3, calculate the next state which is generated because of these equations. If it's a part of the valid sequence, then we say that it's self-correcting counter. By chance, the 4, let's say the 4 leads to some other number. 4, let's say 4 leads to 7. By chance, 7. So then you cannot come to the conclusion it is hang up state. Again, you have to take a 7 and find out what is the next state. So if by chance after the 2 clock cycle, if it enters the valid state, then also we can call it as self-correcting counters. Sometimes in some sequences, self-correcting counters cannot come to the valid state in a 1 clock cycle. It may take more than 1 clock cycle. So such case is also self-correcting counters. Only thing is, if it hangs up in 2, 3 states and it will be rotating in those sequence only, and those sequence is not part of the regular sequence, then we say it's a hang up or a lockout situation. So how to design in the beginning itself a counters which are self-correcting in nature. So we will do such one design now. So we will take up this is the state diagram for the previous counter. So normal sequence was given. Now the new thing entered is what 7. So when we say 7 state, it will enter into valid state. So the 4 is invalid state, it will enter to this one. So this indicates that it's a self-correcting counter. This is how we can represent the state diagram. Now, so let's start with how to design a counter which is self-correcting from the beginning itself. So let's design one such counter. Now, so design the mod 6 self correcting counter using T flip-flops. So we will use the T flip-flops in this case. So let's take the same sequence what we used in the previous one. Only thing we'll make it as self-correcting and we use a T flip-flops. Now, so we'll prepare excitation table. So excitation table has got 3 columns. The first column is the present state. The next column will be the next state. The third column will be the flip-flop inputs. Now, so since 3 flip-flops are there, so Q1, Q2, Q3 will name the flip-flop outputs. The sequence given is written here 0, 1, 1, 1, 1, 0, 1, 0, 1 and 0, 0, 1. These are the required sequence. It is given in the here. So it is a required sequence given here. Now, so I will write now what will be the next state for these states. So it is Q1 plus, Q2 plus, and Q3 plus. Now it is 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, and then 0, 0. So how we are written? Second become the next state for the first state. So third one will be the for the second one. Like this we have documented it. Now there are two states which are not part of this sequence, but they are part of the three flip-flop states, all possible states. So we will write those states which are invalid or not part of the sequence of states. So 1, 0, 0 is a 4, which is, so the decimal value of that 4. So another one is 7, so 1, 1, 1. Now what is the next state we will take for this? There are two options there. Either I can take the next state for the 4 as the initial state 0, 0 I can write down. Other option is sometimes the designers or the people who has to design this type of counter, they will say that take the next state. So for the 4, the next state will be the 5. So I can write here 5, 1, 0, 1 I can write it. So similarly for the 7, I can take the next state as a 0, 0 or the next to 7, that is also 0, 0. So here I'll assume that the next state for the 4 will be first state 0, 0, I'll take it. So 0, 0. Based on the question, you can choose what is the next state for the every invalid state. Now here also I have taken a 0, 0. Now, so now we have to write the flip-flop inputs T1, T2 and the T3 because T flip-flops will have only one input, that is called T1, that is called the T input, toggle input. Now to fill the values of T1, T2, T3, I should know application table of a T flip-flop. So let's write application table for T flip-flop. So this is Q and the Q plus, and what will be the value I am supposed to give to the T input to get the sequence. Now all combinations I'll write it 0, 0, 1, 1, 0 and the 1, 1. We know that it's direct, it's very direct in case of a T flip-flops. So if the current Q is 0, the next Q plus should be also be 0, means don't toggle it, make it 0. Current is 0, the next state is 1, you want, toggle the flip-flop, allow the toggling. So same thing for here, 1, 0, I return it. So now we have written the application table for T flip-flop. Using this, I will write now what is the required values at the T1, T2, T3 to get the required partition. So required change in the state. So I'll take the first Q1. So it is 0. So I want to change it to 0. So this will be 0. This is 0. I want to change it to 0. So it will be 0. 0. I want to change it to 1. So toggling is required. Similarly 1, 1. So no toggling is required. 1 and it is 0. So toggling is required. 0 and 0 and 0, 0. So no toggling is required. It's a 1 invalid state. So and then it should go to 0. So toggling is required. So 1 and then it has to go to 0. So toggling is required. Similarly, we will write for now the second second flip-flop. So Q2 is 0. The next expected 0, 1. So toggling is required. So 1 to 1, no toggling. 1 to 1, 0. 1 to 0, 1. So 0 to 0, it is 0. So 0 to 0, it is 0. Then again 0 to 0, it is 0. So 1 to 0, toggling is required. Similarly, now we'll write for the Q3, that is the last flip-flop. So 0 to 0, so toggling should be 0. So 0 to 0, so 0 to 1, it is a 1. 1 to 0, toggling is required. 0 to 1 required. So 1 to 1, 0. 1 to 0, toggling is required. Now similarly 0 to 0, it is 0. So 1 to 0, toggling is required. So now we have written the excitation table for the T flip-flop. So now let's design the or derive the algebraic expression for T1, T2, T3. So let's write the key map. So Q1, Q2, Q3. This is 0, 1, 0, 1, 1, 1, 1, 0, 0, 1. So it is a 0, 1, 2, 3, 4, 5, 6, 7. Similarly, so I will write for next flip-flop. So this will be for T1. So this will be for T2. So this will be for T3. So now I'll fill the values. So for 0, so you can write the cell number here. For cell number here, for example, 0, this is 2, this is 3, this is 6, this is 5, and this is 1. Now for the 0 cell, the required value, so it should be 0, 1, 0. So 0, 1, 0. Similarly, for the second cell, so 2, it is 0, 0, and then the 1. Similarly, for the third one, so you should look at 1, 0, 1. So third one, 1, 0, and then the 1. Now look at the sixth cell. For that, output is 0, 1, 1. Sixth cell, 0, 1, and then the 1. Now for the fifth cell, it is 1, 0, 0. Fifth cell, 1, 0, and then the 0. Similarly, for the first cell, so it is 0, 0, 1. So first cell, 1. So it is 0, and then the 1. Similarly, for the invalid state, fourth cell. Earlier, we were taking as a don't care condition. Now we will fill with the required values. Fourth cell, 1, 0, 0. 1, 0, and then the 0. So 7, it is 1, 1, and then the 1. So it's very important. If you fill the don't care, circuit will be simplified, but there is a chances of getting into invalid operation. So it's better always make every state predictable. That means that when it enters into any invalid state, it should be predictable behavior should happen. Now, so let's group the values. So it's a 1, and this will be another group possible. So T1 is equal to Q1, Q2 bar. So this is Q2 and this is Q3. Similarly, T2 equals, so here's 1 and there is another 1 group possible here. So it's a Q1 bar, Q2 bar, Q3 bar plus Q1 and the Q2. Similarly, so here, so there's a one grouping here and there's another grouping possible here. So if you write for T3 equals Q2 plus Q1 bar dot plus Q3. So now we have got the expression for everything. So using these equations, algebraic equations, we can make the connections for T1, T2 and T3. Let's observe that in the logism. Now I have made all the connections as per the derived expression. So T1 is equal to, if you observe the T1, if I click on the T1, so I'll go to here. So if I click on the any one of these, for example, so this expression is a first expression Q1, so it is a one expression Q2 Q3, other is a Q1 Q2. Similarly, so I have an expression for here this one and then expression for this one. So that is Q1 Q2. You can see that Q1 bar, Q2 bar, Q3 bar, and this is an expression like this. So based on the expression what we have received, I made all the connections. Now clock of all the flip-flops are together and given to a common clock because it's a synchronous counter. Now only thing is for the preset, I have just made, I given a 0 0 0 0 means it's an active high, so that preset will not be affected. I'm using this presets to induce a error state. Now let's verify the normal operation now. So we know that, so it is working properly. Now 0 is the first state, then 2 came, so then the 3, so then it will be 6, so then it will be 5, it's correct. So then after the 5 it's a 1, and then it becomes a 0 and continues. That means that as per the design, the synchronous counter mod 6 is working. Now let's see the invalid state. Is it working properly or not? Is it giving stable condition? Now 1004 is an invalid state. So now what I will do is I will drive the flip flop to the 0 state. Now I'll induce the 4. So how do you induce the 4? You can use a synchronous input. Make it 1 and then 0. So now I have induced 100. So 4 is not a valid state. Now I'll give a clock pulse and see that as per our design, 4 should lead to 0. So it lead to 0. That means that, so our design is correct. Now I'll induce a 7. So I will induce a 7. So I'll make this as 1 and then 0. So 1, 0, 1, 0. Now I have induced an error state called 117 state. So now I'll give a clock. We have designed 7 should enter into 0. So give a clock. It is 0. That means that the counter what we designed is a self-correcting counters. It generates all the counting sequence, and whenever it enters invalid state, it's getting to the required next state. So this is how synchronous counters are designed.